Great. I have to say that we are all aware of that. Okay, and today it's my pleasure to introduce François-Xavier Désert. François-Xavier did his PhD in 1986 at the Laboratoire de Radioastronomie of the University of Paris. Then he moved to the Goddard Space Flight Center as a postdoc, and then to the Leiden Observatory as a postdoc as well, before coming back to France at the Meudon Observatory as an astronomer. And in 1997, he became a faculty at the Institut de Planétologie et d'Astrophysique de Grenoble. He has been the director of the Institute between 2015 and 2020. In 2008, he won the CNRS Silver Medal. So he's currently an astronomer at the Institut de Planétologie et d'Astrophysique de Grenoble, and he's also a COBE visitor until the end of July. Yep. Yeah. And his main research interests are the interstellar dust, the CMB, and the clusters of galaxies. And today he's going to talk about Planck theme and variations. And now you have to hear this. So, yeah. And I hope everybody online can listen to us. Yeah, you can remove your mask as well. Okay. Thank you.
Can you tell me if you hear me?
Sure.
Hello, everybody. Can you hear me? Yes? Yes. Okay, and remotely, probably?
Yeah.
I hope.
At least no one is complaining.
Okay, no one is complaining. So I was asked to give a seminar about any topic I wanted. I didn't have any constraint, so I decided to talk about Planck and the two sides of Planck and the Max Planck, famous physicist, and also the satellite. And so I will keep moving back and forth from these two positions. And I will refer to Max Planck as the human being and Planck as the satellite, for short. So I just wanted to thank the organizers. So I had all my notes about whom to thank. And I don't have my notes present in front of me, so I will improvise. So thank you for the organizer for giving me this opportunity to talk about my work. I thank George, Anthony, and Roberto for inviting me to COBE Institute. I'm very honored with that. And I thank the Churchill College and the French Embassy in London for giving me that opportunity to spend 6 months in Cambridge. Probably I forgot people to, anyway. So I'll make some advertisement about a nice talk tomorrow at 12. Is that correct, George? Yeah. I don't know whether it will be nice. So please reserve the hard questions for him. I will answer the easy questions today. So I will not talk about the cosmic camembert. I think you call it the cosmic pie, but it's depending on which side of a channel you are from. And the composition of the universe, I have nothing about that today. And I want to talk about the Planck blackbody radiation and how it is central to what we are doing in the millimeter domain. So my general talk will be about what we measure in millimeter wavelengths, typically 300 gigahertz, for people who talk in frequency rather than wavelength. And so to introduce the subject, I will talk about the Planck radiation, and it has a very specific spectrum. And as you can see, maybe I can point that to you. Okay, the Planck function is quite generic, and it has a form, a prefactor, which is in mu cube, which is the place where you can put photons. And then there is a general function, which is the occupation number, which is simply 1 over e exponential x minus 1, where x is the reduced frequency. And you can see it is reduced because it's h nu divided by kT. So the blackbody, which is in equilibrium, in thermal equilibrium, will emit radiation according to that law if it's 100% emissive. And the x here, I have scaled to the 3K background. And typically, x is several units where things happen here in that expression. And so if you represent that function, the the photon occupation number. So in fact, I plot x times f to make it flat. And this is called the Rayleigh-Jeans part. So at low frequency, you are in the Rayleigh-Jeans part. And at high frequency, you have what is called the V part. So the exponential tail, where it goes to 0. And also I've worked on the deriving that function relative to the temperature. And you get a more complex derivative. And I'll show you that, in fact, you need to go to the second derivative, and we measure that very accurately. And the second derivative is the function of g, which is the first derivative, times a new function here, COTH, so in reciprocal TH. This function is very important, as you will see, for the Senya-Zeldovich effect. So once this is introduced, I want to do some history. So I'm not a historian, but I took some interest into digging into Max Planck's life, and it's horrible. He had a terrible life. So may I, and especially for students, I hope they are not frightened. So in 1887, Max married Marie Merck, and they had 4 children. So far, so good. Several happy years. And in July 1909, Marie Planck died, possibly from tuberculosis. So I have an aunt who was ill with tuberculosis, and it was really bad. And nowadays, we don't talk about tuberculosis anymore in Europe. In March 1911, Planck married his second wife, and in December, his 5th child was born. During the First World War, Planck's second son, Erwin, was taken prisoner by the French in 1940, while his oldest son, Karl, was killed in action at Verdun. So I pay respect to his to Planck's sons. And Grete died in 1917 while giving birth to her first child. It was quite common for women to die giving birth. I think it's not very common anymore. Her sister died the same way 2 years later after having married Grete's widower. Both granddaughters survived and were named after their mothers. And Planck endured these losses stoically. In January 1945, so we are going to the Second World War, Erwin, to whom he had been particularly close, so his son, was sentenced to death by the Nazis because of his participation in the failed attempt to assassinate Hitler. Erwin was executed in 1945. So, but Max Planck is remembered for what he did for physics, and the fact that photons are particles, can behave as particles with an energy which is h times the frequency. And that was the birth of quantum physics. Okay, and I found also this picture, which is very nice, and which is taken, my notes are really missing, in 1925. And so you have a sort of collection of great physicists, and they are all Nobel Prize. So I have the date, and so the earliest is this one, Maxwell Knoll, for diffraction against solid. And then you have Nernst, Einstein, Planck, and Millikan. The fact that the charge comes in elementary units. And so if our students, I would like them to note something particular in this photo. What do you notice? No woman. Yes. All right. There is no computer, there is no paper. It's all in the brain. So we are talking between each other, and you can imagine the discussion they had together. And also, it's not very COVID oriented. They are packed. Anyway, so why do I talk about the blackbody radiation? It's because we have an almost perfect blackbody in the sky, and it's surrounding us, and it's at very low temperature because it has cooled down for a long time. So between Z equal 1000 to 0, And so at the time of its emission, it was at 3000 Kelvin, almost like the sun. But because of the expansion of the universe, now it's 3 Kelvin. And there were a lot of questions. So Penzias Wilson, Nobel Prize, discovered that radiation. And after that, there were a lot of discussion about, is it the spectrum of a black body? We didn't know if it was a black body. And so John Mather presented the data from the COBE instrument, COBE satellite with IRAS instrument, and the data showed a perfect black body. And these data were taken in 9 minutes of observation with COBE. So that was the end of it. The radiation, the 3K radiation, is a perfect black body. So this discovery was made with an instrument that contains 4 detectors, or 2 detectors, and with a Michelson interferometer, which is a Nobel Prize, who is the Nobel Prize 1907. And John Mather became Nobel Prize in 2006. So it's full of Nobel Prize here. It's shining very hard. And so, in fact, it's the curve I showed you has never been measured. What IRAS is doing is a sort of double differencing. And so what we measure is a kind of 0. And the temperature now, after John Mather and his team worked very hard on the thermometers, they have come down to this level of precision for the temperature of the CMB. And it's 2009, while COBE was launched in 1990. So it shows the long term. Okay, now another sad event. And I will be finished with history after that. So he's not a well-known guy. He's called the von Mosen guy, and he was one of the first students of Max Planck. So I read that because it's full of history. So Kurt Mosen guy was born in 1884, and he was a student of Max Planck. And in 1905, Max Planck became the most prominent early advocate of the theory of special relativity of Einstein. In subsequent years, Planck published several works in which he explained further consequences of Einstein's theory of relativity. He conveyed his enthusiasm to his assistant, Max von Laue, future Nobel Prize, and his student, Kurt Mosen guy, who became the first physicist to habilitate and graduate, respectively, in relativity relative system. So tragically, I hope it's not the case for many PhD students, Kurt died in a mountaineering accident before he completed his PhD. So another death surrounding Planck. I don't know, but Planck was surrounded, he lost half of his family. And here he even lost one of his PhD students. So, but still, Planck and Wien published his PhD. And this is the case where you want to talk about what happens if you move towards a black body. So you're surrounded by black body radiation around you. What happens if you have a velocity with respect to that black body? And so Kurt von Mosen guy was the first guy to write down properly the equation in relativity. So I think we should call the Doppler effect on the CMB, we should call it the Mosen guy effect in honor of his student. And indeed, this is what we see when you look at the sky at millimeter wavelengths. The first thing you see, so this is an all sky map. The first thing you see is that the map is slightly hotter on one side and slightly colder on the other side. And this is called a dipolar effect. Okay, so you can guess the galaxy. The galaxy is emitting a bit in the plane of the galaxy here. And in fact, you can see it better once you remove the so-called dipole effect. And so the so-called dipole effect is just a change of temperature due to the Doppler effect of our motion relative to the black body. And in that effect, you see that there is a velocity term, u. So this is the total velocity that you've got. Now, when you are traveling with the Earth around the sun, you have what is called the orbital velocity. And so your velocity will change every 6 months from one side to another, whereas the global velocity of the solar system will stay always the same. And so you can see that this effect is very important to calibrate an instrument. And I can show you, I'll talk to you about that. So this COBE experiment gave this map with a rough idea of change of temperature from one place to another. And this map was made much more precise by WMAP 10 years later. Okay. And then there was a Planck satellite launch. Say it's the 3rd generation satellite. And I will talk about that a little bit now. And so this launch was on the 14th of May, 2009, and by Ariane rocket. And we were the little dwarf with Herschel on top of us. And we were quite frightened that it would squash us, but it didn't happen. So the two experiments were together measuring the sub-millimeter sky, and they separated half an hour later very nicely, and they went their own way to L2 Lagrangian 2 point, some 1.5 million kilometers away from the Earth. So I had a whole history again about this date. So I looked in my history book about what happened on the 14th of May. And 399 years ago, something happened on the 14th of May. And it's Ravaillac who killed Henry IV in France. And I'm sure George doesn't know that. This happened 50 meters in the street, 50 meters away from where François Boucher lives. So you look it up. So there are coincidences in that date. I like to remind people. Anyway, so we are back to, so that killing had huge consequences in Europe, because that's the time where Huguenots, so Protestants, went away from France. And we lost smart brains to England and the Netherlands, and they never came back. So Planck results, that will be shown tomorrow by George, but still I will show one map. So here you see an old sky map where you have tiny fluctuations of temperature from one part to another. So the red is slightly hotter by a few tens of microkelvin, and from one place to another. And so this has been measured to a very high accuracy by Planck, much better than WMAP, but WMAP was much better than COBE, and so on. And we could even measure polarization. So this is the same map in intensity, but smooth to 1 degree. And you can see the little dots, the little rods, which are showing the polarization of the sky. And so that was a feast to understand what happened in terms of polarization of the sky. And also we were able to measure the matter fluctuations across the sky. So Anthony is a specialist of that. He probably told you a lot about these maps. So I come back to the Planck function first derivative. And to first order, you see our displacement with respect to the blackbody at rest. And so this Doppler effect can be decomposed into two velocities. So the first velocity is orbital, and it's by typically the velocity of Earth around the sun. It's 30 kilometers per second. And so you expect, simply by plugging the temperature of the CMB, you expect 271 microkelvin. And this is exactly so. This is what we use to calibrate Planck. We use the annual variation of the signal in direction to measure, to calibrate the detectors. And then we can deduce from the overall effect the dipole, and this is measured with an accuracy which is staggering, so within 1 microkelvin. And this measures the solar system velocity with respect to the standard of rest, which is now where the black body is a real black body in all directions. And the velocity we get is 369.8 plus or minus 0.1. So it's very accurate touch. And even there is another paper where the precision has been improved, but you see the direction of the dipole converging to a single point, and the intensity of the dipole converging to 3,362. Okay, and even the Doppler effect can be seen in the fluctuations. So you expect that the fluctuations will be a bit brighter on one side and shallower on the other side. And this is indeed used to find what's the dipolar structure of the fluctuations themselves, and they converge to the same point as the dipole himself. I find it gives a very consistent picture of what we are seeing with the first derivative of the Planck function. Okay, I don't resist to show you also the maps which have been obtained by Planck at different wavelengths. And you see the frequency here. And at very high frequency, you're dominated by galactic dust. And when you go to low frequency, you're dominated by synchrotron. And in between, typically 217 gigahertz, you see the fluctuations here appearing. So you have a huge work to do to disentangle what are called the foregrounds from the CMB fluctuations. Okay, so I will talk a bit about galactic dust. And this is the spectrum of dust as measured by FIRAS. So it looks like a black body, but in fact, it's a modified black body. So the fact that it is a modified black body can be understood this way. So you have a radiation field coming from all the stars, and the tiny solid particles are absorbing light, and they are heated. And normally, if they were emitting like a black body, they should be at 3K. Why 3K? Fabry noticed that the interstellar radiation field was of the order of the equivalent of a 3K background. It's just a coincidence that it's the same temperature as CMB, but it has nothing to do with it. And so the grains should be at 3K, but they are not, they are at 20K. Why? Because the grains are small particles, typically 0.1 micron, and so they are completely unadapted to emit at 1 millimeter. And so they will emit badly. And the fact it is badly means there is an emissivity which is low, and they don't emit like a black body. And so you have another factor, an additional factor, which is the spectral index of dust. And so Planck has been refining the temperature of dust, measuring the temperature of dust and the spectral index. And there are many subtleties to understand why they are not exactly the same as we iterated the analysis. And even in polarization, there is a tension with intensity, and we don't completely understand what's going on there. So it's ongoing. So I want to go to instrumentation now. So to realize the feast of Planck that was done with bolometers. And I must salute Jamie Bock and Andrew Long. Andrew Long is now not anymore. And they were fantastic guys who made very accurate detectors. And in Planck, we have just 52 bolometers, 52 detectors for HFI. And these detectors, they measure the 3K background with little spider web here, which are above a bath, which is 100 milli-K. So you can understand why we need very low temperature, because the 3K background is very cold. So if your detectors are too hot, they will have too much noise. And so we needed to have very low temperature in space. So Alain Benoit made an open dilution. So by mixing helium-3 with helium-4, you get some cold at this temperature without freezing. And we have said that Planck was the coolest place in the universe because of this 100 milli stage. And these detectors were fantastic. But they had little problems. So unfortunately, I show this picture because I worked 10 years on that topic. So which is the detectors, they detect photons, but also they are sensitive to cosmic rays. And in fact, we almost lost Planck mission because there are so many cosmic rays. And you see for a dark bolometer that shouldn't see anything, it was seeing glitches all the time. So this is 3 minutes of data for 3 detectors. So the dark detectors, the dark detector can only see glitches. And then at high frequency, you see when you cross the galaxy twice every minute. And then at low frequency, 143, you see the dipole. It's obvious. It's a cosine function of the time. As the telescope is rotating and scanning the sky, we see a sine wave. And this is the work we do after processing. That's what we get. So we remove painfully the glitches to arrive at something that can be projected on maps. So I wanted to show you that even the best detectors have some drawbacks. And so I like the detectors very much, but only 52 detectors on Planck. So can we do better? And the answer is no. Each detector on Planck was the best, and they were at the limit of the photon noise limit. And you can't do better than the photon noise limit. And the photon noise is coming partly from a 3K background. So you can't get out of a 3K background. So these detectors were perfect. So how can you do better? Is either you integrate longer, or you make more detectors, and you make arrays of them. And so to make arrays of them, you need to read these detectors simultaneously. And so these people have devised detectors which are not bolometers anymore, but which can be multiplexed with a large factor. And so they are called kinetic inductance detectors, and they work as a supraconductor device, which inductance changes when photons hit them. And so in that case, this was invented by Peter Day in Caltech in 2003, and they didn't use it for astronomy. And it was revived by Simon Doyle in Cardiff, and with the help of Alessandro Monfardini in Grenoble, that was made into astronomical machines. And that's what I want to show you. So maybe I'll skip that. So I want to sort of, which should you bet in the future between these detectors? So either thermal detectors like bolometers that were used on Planck, that have been used in many instruments on the ground, or kids. So kids are less mature, but they are coming fast and furious in from every laboratory in the world. And the main thing that you have to retain from kids is that they are easily multiplexable. So you can have less wire coming out of your cryostat. Anyway, so I won't spend too much time. So we decided to make an instrument out of kid arrays. And for that, we assembled many people. And the PI were Alain Benoit and Alessandro Monfardini in Grenoble. And I've spent a lot of time helping them building that instrument. And you notice that Cardiff has been very active in that program. So we started in 2015, and now we are in the stage of large programs. So we are observing large programs. We have 60% done. And so I will show you what I'm talking about. So NICA 2 in a nutshell, it's one slide showing you what it's made of. So the telescope, it's 30-meter telescope in Spain, in the southern part of Spain at 2,870 meters. So it's good for millimeter astronomy. And we use a keyed array. So here you can see 1,000 pixels. Each pixel is typically 1 millimeter, the size of a wavelength. And you see that we have only 8 readout electrons. And so that's the multiplexing is there. And these arrays are put at the focus of the instrument that you can see here. So this instrument is several tons, which is placed at the focus of this telescope. And it's a camera at several wavelengths. So we have a camera at 2 millimeter and one at 1 millimeter. And the characteristics are that we have a large field of view, thanks to the large array. And we have a very good beam for a single dish instrument with 20 arcsecond. I remind you, Planck is 5 arc-minute. And in NEFD, so the sensitivity are quite good. And we have a very large mapping speed, thanks to the number of detectors. So I show you examples of what has been realized with this instrument. This is a map of a galactic plane. So it's typically 1 degree, 2 degrees. And this is 1 millimeter map. And I will switch back and forth. Sorry. So this is 2 millimeter. So this is acquired at the same time. There is a dichroic. So we measure the 2 wavelengths at the same time. And you can see the close resemblance of the two. The beam is not the same, but they do resemble each other. And just to show you the comparison with other instruments. So this is the infrared map. And this is what we get with Gaston. So it's the large program with NICA 2. And what has been obtained by other instruments with a reduced angular resolution. And this one is at a different wavelength. And you can see the degree of precision that we obtain. And with the little clumps, so each little clump is probably on the verge of forming stars. So I will skip the analysis of this. And I want to go to that point. In fact, the measurements on the ground are limited by what we call sky noise. And so we have difficulty retrieving the large angular scales. So now the aim is to use Planck as the truth for the large angular scale and combine that with a small angular scale that we get with these cameras. And one example has been done in the center of our galaxy. So this is a combined map between Planck at large scale and LABOCA, which is an instrument in Chile. And you can see the amount of detail is remarkable. So the high dynamic map can be obtained by combining different instruments. So that will be done with NICA 2. I'll skip that. So this is another program with nearby galaxies. So you recognize spiral arms at 1 and 2 millimeter. And so this is a program to map nearby galaxies in the millimeter domain with high precision. Also, we have done deep surveys, so looking for high redshift galaxies. And so our aim is to reach the confusion limit. So you can't go down, you can't detect more sources because they are all walking on each other's steps. So that's the confusion. So we aim at the confusion limit in the Goods North field and a bit shallower in the Cosmos field. So this is the characteristic. So with an M2CLS large program with NICA 2, we aim at large array. So I can't show you the result of that deep field because it's still being analyzed and improved, but we have a small deep field that was done accidentally. So Lestrade was looking for a debris disk, nothing to do with high redshift galaxies. So he was there is a star here, and he was trying to look at debris that would be a signpost of maybe planets. And in fact, he found this ring of sources 10 years ago. And he said, maybe it's an inclined disk around that star. So we re-observed 10 years later, and the sources haven't moved. They should have moved because the star is moving in the plane of sky, and they didn't move. So these sources are real extragalactic point sources at high redshift, and they are on the string. So we wonder if it's a cosmic filament or not. But at least we've detected Millijansky type sources at 1 millimeter. So now I would like to, how much time?
15 minutes, maximum.
15?
Yeah.
Okay. So I'll go fast. My main interest also is the Sonia-Zeldovich effect. So we have, I want to tell you about the SD effect. So you have a cluster of galaxy, which is full of, the baryons are dominated by hot gas, millions of degrees. And this hot gas is scattering the sloppy photons, the sloppy 3K photons. And this scattering should produce zero result. If you are going with me with a Doppler effect, you have as many electrons going one way and as many electrons going the other way. So the Doppler effect should go to zero. And indeed, it's almost the case. So you have to go to the second order of the derivative to find the SD effect. And indeed, it works. So the second order will be proportional to the square of the velocity of electrons. And the square of the velocity is the temperature of the plasma. And indeed, the effect that we find is that we have an integral of the temperature times the density of the medium and times the line of sight. And so we are directly measuring the pressure inside clusters thanks to the SD effect. And so this is, I come back to the second derivative, so the famous h of x. And here you notice it's not -1, it's -4. So why, it took me 6 months to figure out why is -4. And there is an effect in scattering, you don't create photons, whereas the second derivative can create photons. So in order to balance and to make it a real scattering effect, you need a slight change of the temperature of the microwave background. And so that's the -3 is coming there. The -3 comes from the fact that when you're counting photons, the number of photons is proportional to the T cube. Anyway, so H-4, the -4 is important because it makes what we call a SZ decrement at a millimeter wavelength. So the cluster should appear as a negative brightness at millimeter wavelengths and positive brightness at sub-millimeter wavelengths. And this is exactly what we observe. So this is the Planck map of one cluster. And you can see that as a function of frequency, the cluster is negative. So it's not that you have negative light. It's just with respect to the CMB background, which is very intense, you see a slight fluctuation, which is negative, and which has a 0 at 217 gigahertz here, and is positive here. So a beautiful example is given by COMA cluster. So this is in the visible, so you get 1,000 galaxies, but in the millimeter domain, you are dominated by the hot gas, which is scattering photons. This is the SZ effect. And in color, you see Planck map. And in contours, you see the X-rays, which are also sensitive to the hot plasma. So with a small kid array, we managed to detect, so this is a map here. We managed to get the first detection of the SZ effect. So that was in 2014. So if you are a PhD student, if your name starts with A, then you will be very famous. Because I will show you the next. Okay, I'll skip that one. but this Rémi Adam is really good, but he signed the papers, but he was the first one, and he has made excellent job anyway. And so here it's the first map of a kinetic SZ effect, which is a second Zajdovich effect, which comes from the fact that if a cluster has a global motion, you can detect its line of sight velocity. And so this shows, this map here shows that subcluster B is moving away from us, and subcluster C is moving towards us. And the velocities are big, a few thousand kilometers per second. So it's the first map of the KSZ done, and this was done with kids. And we see the collision of three subclusters. So this is a very messy cluster, but very bright. And on the same cluster and the same student, he has got a permanent position now. And by comparing with the temperature map, we can get our own version of the temperature of a cluster, and you can see that it is quite changing from 10 keV to 20 keV. So we can see shocks in clusters. Yep.
So how did you subtract the primordial CMB?
That's a good question. The primordial CMB is like a gradient on our map, because here, look at the scale, it's arc seconds. So basically, it's so smooth that we never detect the CMB. Sorry. And so there is a large program for SZ effect on about, we wanted to complement the catalogs of SZ clusters that were provided by Planck, ACT, and SPT. So these are big instruments that now the SZ is becoming an industry. And we want to use the clusters as a probe of cosmological parameters. And you can see how here it's measuring some quantity. I will not have time to discuss, but a quantity that describes density of matter. And you can see that the SZ effect can provide interesting constraints, although a bit at odds with what the CMB is providing. And so we want to improve on that diagram. And for that, you need to calibrate these clusters so that you can count them properly, in fact. And so that our aim for the large program SZ was to calibrate the relation, so to make this prediction more accurate here. And so we selected high redshift clusters because we have high resolution. We can measure clusters which are small on the sky. So I skipped that. And so the idea is to measure the temperature of clusters and the hydrostatic mass. And from the hydrostatic mass and the quantity measured by Planck, we get the Y-M relationship. Okay, I'll talk about also problems. So this is one cluster that has been published by another PhD student. And this cluster, this is the SZ effect that we find. So this is the decrement of temperature that we measure at 2 millimeter. And you can see that it's not very round. It's not very spherical. And at 1 millimeter, we are bothered a lot by point sources. And we don't think that the point sources belong to the cluster. We think they are in the background, and they may be or not amplified by the cluster. Anyway, this is the model we make out of SZ effect plus sources, and this is the residual for the 2 millimeter part. So we have to take into account point sources when we measure SZ effect. And Planck cannot see the point sources, so it's biased by point sources. So we need to evaluate that. I think it will be important. And another thing that we can do with NICA2 is to measure the temperature again here. without having access to the temperature as measured by X-ray satellites. So we can compare. It's quite interesting. So shocks again. The future of LC experiment is to measure the birth of clusters. I hope you can see it. So it will appear. So this is a simulation of how clusters form and how the SZ signal increases as you go along with time. So you see the redshift here going down. So you accumulate all the clusters being formed. And you can see that counting cluster means something. With different parameters for the universe, you will not have the same number of clusters. So it's a probe, cosmological probe. So we are thinking at Grenoble on how to make large survey of clusters of galaxies in LC domain at higher angular resolution. So this is just a simulation of what we could observe in a 300 square degree. And you can see individual clusters, but it's all here full of clusters of galaxies. And we could measure the kinetic SZ effect and measure how the mass is moving around. So that's what we're thinking about right now. And my idea would be to start detecting the cosmic web and filaments separating clusters. So doing the TSZ outside clusters. Right. So if I have 1 minute, can talk about Concerto. Sure. So in another development, Guylaine Lagache has started working with the Grenoble group to make an instrument that would measure the primordial carbon, or primordial. They say the first carbon produced by stars in the early universe at Z equals 6. And that carbon would produce a line in the millimetric domain. So you need spectroscopy. And so for that, Alain Benoit and Alain Monfardini have devised what we call a Fourier transformed spectrograph. And this is mounted here at the Apex telescope in Chile. And in the instrument, you get, now I think you recognize that you get 2 arrays and a total of 4,000 kits, which are measuring the spectrum in the millimeter domain. And this is the first map that was obtained by Concerto last year. And I take part in the calibration. And it's a nightmare to calibrate a spectrum graph, I can tell you. So just to show you the number of pixels increasing every year with new instruments, with kits. So I think kits is a very promising technology for future of astronomy in the millimeter. And to conclude, am I correct? So I think we have expanded Max Planck's heritage to high precision physics, and the CMB is a treasure trove for the Planck function, and we use that every day. And the Planck satellite has given us a legacy, and it was only a 1.5 meter telescope, and so we can improve on Planck, we can complement Planck by having much bigger telescopes and much bigger arrays. But we still use Planck. Planck is our first information, and we just complement Planck by going to higher angular resolution. And my final word is that discovery comes from innovation, but also from people. Okay. Thank you very much.